So in unification scheme, we will continue with neutrino oscillations and we'll look into some more details. This information that I'm reading out right now is actually published in the Nobel Prize website, and it talks about more of the basics of the discovery of neutrino. Well, the SK collaboration in Japan actually gave a lot of proof about the existence of neutrino. It also said that the disappearance of the atmospheric muon neutrino, that is the neutrinos when produced during the cosmic ray, interact with the atmosphere as they travel from their point of origin to the detector. And in this course of interaction, the type of neutrino, the possibilities are there that it changes. In the later years, 2001-2002, the Sudbury Neutrino Observatory collaboration actually published a very clear evidence for the conservation of the electron type neutrino from the sun to muon or tau neutrinos. So the conservation principles or laws were published by that time. So the electron type neutrino was existent and actually originated from the sun when we talk about the atmospheric neutrinos example. We also talk about the solar neutrinos here more specifically. So these discoveries were actually of very much fundamental importance, and it constituted a major breakthrough because it allowed us to prove a lot of equations which initially looked to be not conserved. So neutrino oscillation and the connected issues of nature of the neutrino masses and possible CP violation, charge parity violation among leptons are today the major research topic in particle physics. So if you are really going into particle physics and doing any kind of research, mostly you will talk about the nature of the neutrino or talk about the neutrino masses, because it is still not determined properly. The standard model doesn't talk anything about neutrino mass on top of that, and of course there is a possible CP violation which also needs to be studied more. So if you look into the existence of muon neutrino, it was actually established in the year 1962 at the Brookhaven National Lab, okay, and it was established using neutrinos from the pion decay and demonstrating occurrence of the reaction. So if you look into a reaction something like this, where we have an antineutrino, a proton, muon and neutrino, okay, so proton gets converted into a neutron, sorry, not neutrino, proton gets converted into a neutron with a muon, okay. This was observed, but on the other hand, if you look into the antineutrino and proton getting converted into a neutron with a positron, now this was not observed, okay. So this is something which was not observed. So that means there is some kind of disbalance. So it was said that the muon neutrino and the electron neutrino, okay, more or less were indistinguishable, okay, and the rates of these both reactions should be equal. So both these reactions should be equal, okay, and then Lederman, Schwarz and Steinberger were actually awarded the Nobel Prize in the year 1988 for this discovery. So they actually discovered that the reactions should more or less be equal in nature, okay. So what happened with the solar neutrino is that where there are thermonuclear fusion reaction which is actually happening at the core of the sun, and then there is generation of a lot of energy and of course neutrinos. So if you look into the solar neutrino problem, it basically refers to the observation that compared to theoretical predictions. So there were theoretical predictions and the experimental observations, and both were allowed to actually get connected, okay. People start to study the connection between the two, and was seen that the flux of the neutrinos from the sun measured on the earth appears anomalously low. So the amount of neutrinos reaching from the sun to the earth has become very low. Now this problem persisted for more than 30 years before it was finally resolved by measuring with the heavy water detector at the SNO observatory. So what happened was the neutrinos were not being detected, but then finally after 30 years of long wait, it was being detected by using heavy water detector. So how are the neutrinos formed, what are the different stages, what are the other elements which are formed along with the generation of neutrino is very well explained in the PP cycle reaction which we have discussed in our nuclear physics classes. You can definitely refer to that for the reaction schemes. And then we have got the atmospheric neutrino. So when we say cosmic radiation, we are actually talking about the generation of atmospheric neutrino. And then here we actually see more or less the oscillation part very clearly. The earth is usually continuously exposed to a flux of cosmic rays from outer space, that we already know. Now these particles, which are usually protons, as soon as it comes in interaction with the atmosphere, it basically creates a lot of secondary hadrons. Okay, so these protons are actually not alone, they also have got a very small amount of heavy nuclei added to it. So what happens, specifically many pions but also kaons are also produced, which decay into muons and muon neutrino. So we have got pions and kaons, and then they finally reduce or decay to muon or muon neutrino. The muon in turn decays into electron, muon neutrino and electron neutrino. Okay, so these kind of decay reactions are definitely possible. So if you basically have got a pion, okay, pi plus minus, you will have a mu plus minus, and then you will either have a muon neutrino or an anti neutrino, okay, or a muon anti neutrino, depending on whether it's a pi plus or it's a pi minus. On the other hand, you might also have this reaction possible, where you can actually have a muon neutrino getting degenerated into an electron, and then we might have an electron antineutrino or an electron neutrino and muon antineutrino or a muon neutrino. Plus please remember that in the same reaction you cannot have you will usually have basically, let me clear it off, you should basically have a electron neutrino, and if it is a muon neutrino, it will be an anti muon neutrino. Okay, so it will be basically there, or the other way around. So you have to keep this in mind when you actually look into any kind of reaction schemes. So the kaons generate atmospheric neutrinos at somewhat higher energy than pions. So as it keeps on coming from the higher elevation to the lower elevation and comes finally in interaction with the environment, a lot of particle usually disappears. So the charm particle, which actually originates in the cosmic ray interaction, contribute at even higher energies. So even higher than kaons it exists. But if we consider a lower energy and we talk about somewhere near the Earth's surface, the muons usually decay. So the flux ratio, that means the amount of muon neutrino to that of the electron neutrino, is expected to be 2. So that means the muon neutrino would be 2 times that of the electron neutrino, and of course increasing above this value with higher energies. But then down going, as we keep on coming down, the muon neutrino produced in the atmosphere directly above the detector, we see only a few dozen kilometers and are detected at the level expected. So what happens is the muon neutrino is basically detected at that lower level, and then it was seen that there is no indication of the increased electron neutrino flux, and the muon neutrino was observed to be lower in number. So that means this muon neutrino must have oscillated into tau neutrino. So that means the muon neutrino converted into tau neutrino, resulting in something which we call as the neutrino oscillation. The electron neutrino, more or less, the increase in flux was actually not observed. So there are also a lot of unanswered questions there. So if you look into the observation of the quantum mechanical phenomenon of neutrino oscillation, it implies that at least 2 neutrino species have non-zero mass. So we don't know what is the exact mass of each of these neutrinos, but these, out of these 3, at least 2 will actually have a non-zero mass, and the mechanism which generates the neutrino masses is still unknown. So why there is a mass involved in neutrino is still a subject of study, and the standard model basically needs to be extended to look into this physical reality. So we cannot do away with the standard model, it's there, but more extension is needed to study more phenomenon like the neutrino masses and so on. So what happens is, although the mass difference between neutrino flavor has been determined with precision, but no one is yet succeeded in measuring the neutrino mass itself. Okay, so it has been determined, okay, the neutrino flavors, but the masses, it still remains a big question. So that's all in terms of neutrino. In the next class we are going to discuss a bit on string theory.